We present a system for the volumetric acquisition of time-varying, non-stationary gas flows. The invisible plume of hot air above this camping stove has a lower density than the surrounding air, and thus a lower refractive index. This causes the light rays passing through it to bend, which we observe via the characteristic distortion of the background. By measuring this distortion from multiple viewing angles, we can tomographically reconstruct the refractive index distribution, which corresponds closely to other physical properties of the flow, such as its temperature and pressure. In order to measure the heat plume above the candle placed on the sample holder, we used a semicircular array of 16 high-definition consumer camcorders. Each camera is pointed through the reconstruction volume at the background of random noise patterns. To measure the background distortions visible to this camera, we first capture a reference background image and then compute the optical flow, visualized here as a color-coded vector field. In order to perform high-quality 3D reconstructions with a limited number of cameras, we employ a visual hull-restricted tomography algorithm. To compute the hull, we need to robustly estimate the silhouette masks of the flow. Note, however, that a simple thresholding of vector magnitudes results in holes in parts of the plume due to a lack of refraction where rays propagate parallel to the index gradient. This makes morphological filtering unreliable, and so instead we integrate the optical flow fields and then threshold and dilate the resulting pseudo-height fields. The silhouettes define a 3D visual hull within the reconstruction volume. Inside this hull, we use the 2D deflection vector fields to tomographically reconstruct the 3D refractive index gradients, which we then integrate to obtain the final refractive index field, visualized here as a transparent set of isosurfaces. This shows the final result of our system. We can also render the index fields back into the original camera views using a maximum intensity projection. This sequence shows how our method is able to clearly resolve distinct spatial features. Notice that one of the candle flames is weaker than the other two. Here we show novel viewpoints generation for the multi-candle datasets. This is another candle, which is moving under the influence of ambient air currents in the room.